So going then with the proper formal definitions, remember that L squared is actually the magnitude of r cross p squared, but a vector magnitude is really just the dot product of the corresponding vector with itself. So at this point, you see, we are faced with the famous vector identity because this is what's known as the quadruple vector product. So it has the form of A cross B dot C cross D. And there's a general vector identity that tells us what this is. And what it becomes then, what it boils down to, is just you take the dot product across the dot here with the first one with the first one. So you get A dot C. And then you multiply that by the dot product of the second one with the second one, B dot D. And then from that, you subtract off the dot product of these in the reversed order. So A, instead of coupling with C, couples with D. So then you have A dot D. And then finally, you would have B dot C. B dot C, like so. So in our particular case, this works out as follows. I've got the first dotted with the first, which gives me r vector dot r vector. That then multiplies the second with the second, which would be p dot p. And then from this, we subtract off the first dotted with the second one, which would be r dot p, and then multiplied by the second one dotted with the first, which is p dot r. But I'm just going to write it because these are classical variables. I don't have to worry about any commutation relations, just again as r dot p. Now this is a very promising result because look at this. What do I have? R dot r really is just r squared, just like p dot p is just the magnitude of the momentum squared. So I'm getting L squared equals R squared P squared. It looks very much like the sort of thing we suspected we should get, but there's an additional piece that's subtracted off, which is R dot P quantity squared. And if I really want to bring out this idea that we had up above, I would factor out the R squared. That would leave me with a P squared minus. Now, if I'm clever about this, I want you to notice that if I pull out an r squared, that means pulling out one factor of the magnitude of r from each of the two terms in this quantity. So this then would become r hat over r dotted with p. But r hat, and then of course that's squared, and I have to complete my parentheses because I'm pulling out this r squared. But r vector, over r is just r hat. And then if you look very carefully, you will realize what this is this is just the component of the momentum in the radial direction. And that's becoming squared. And so when I take the momentum squared minus the square of the radial momentum, I just want to write this down because we're going to make comparisons with this in the quantum case. It's the square of the radial momentum. What, of course, I'm left with then is the square of the remaining components of the momentum, which is the momentum then perpendicular to the radius, right, or the angular momentum squared. So this actually does give me back to the very simple formula that we learned years ago in our first physics class when we first did rotational motion, but now we have it written out in terms of our proper vector definitions of angular momentum. So our next task really is to ask the question, what happens then when I square my angular momentum operator and try to rearrange it into this very suggestive classical form, and that will help me then relate my kinetic energies to my total Hamiltonian, and then I will be able to make progress on finding the bound states for this three-dimensional spherically symmetric system.